just in case there was any doubt. All right. Okay, so let's start off by talking about the two different types of extrema. So what are the two different types?
Absolute and relative?
Yeah, absolute and relative. Okay, so what's the difference between the two? Like, as we say, we have absolute and relative extrema, but what does that mean? Like, which one is which?
How I compare the two, for absolute, it can be on a closed interval, and it can be endpoints. And FFC is, let's say if we're a minima, it's less than or equal to any point of f of x of the function. And so it'd be like the reverse for the maximum. But for relative, again, for me, I had a tough time with this. How I understand it is it needs to be an open interval. So I do need to see what's happening on the left and the right to judge sort of on like a micro level if it is a low point or like a high point.
All right, nice. That is a very good distinction between the two. And I really like that you mentioned that the absolute extrema is occurring on a closed interval. If it was an open interval, then you're not guaranteed to have an absolute. So that was great that you said that it had to have a closed interval. Okay, and then you're definitely right about the relative extrema in that it's on an open interval. And the thing about this is that it doesn't have to be, less than any other point or greater than any other point. It could just be where things are switching around. So like where the function switches from decreasing to increasing. And then F's for the max, F switches from increasing to decreasing. All right. So let me ask you this question. If you have if you have a continuous function on a closed interval, are you guaranteed to have an absolute max and an absolute min?
Yes.
Yes, that is true. So if your function is continuous and you're looking at a closed interval, there has to be an absolute max and an absolute min. If it's open, then it's not guaranteed. Because if it was open, you could have a situation like this. You have your curve, and then on the open interval, you have open circles on either side. So it's not guaranteed to have an absolute min and an absolute max, because the open circle means you're getting as close to it as possible, but you can never actually actually get to that point. So this one would not have an absolute min, and it would also not have an absolute max. But if it was closed, like that, now you're guaranteed to have at least one. And there could be more, like if there was a tie, but there's got to be at least one min and one max if it's closed and continuous. Okay.
Can I ask a question?
Yeah.
Just for clarification, so on a closed interval, a function has to have both absolute max and min. Is there a possibility it could just like have one or the other? Or
If it no, if it's continuous and closed, it will have to have both.
oh, okay. And then one last question. If there's a function that's just a horizontal line, it's just a constant, would the entirety of the line be simultaneously both like the max and the min every point?
So something like that.
Yeah.
Just going like straight across.
Mm-hmm.
Well, horizontal lines and vertical lines, well, actually, no, take that back, not vertical. Horizontal lines are kind of a unique case because there's no change in it. So it's like the one function that doesn't really fit, kind of have an absolute max and an absolute min, I guess, because it can't be both a max and a min at the same time. So that would be your one exception, but you wouldn't really ask the question like, well, where's your absolute max and min? Because there's only just one value for the entire thing. So this special case wouldn't really ever come up as opposed to like this one or this one.
Okay, thank you.
That makes sense?
Yes, yes.
Okay. So I would never ask you that for a constant function. It would have to be something like this. Or like the one in the quiz was a semicircle or even like a sine or cosine, something where there's some sort of curvature actually happening, where it's continuous and it's also on a closed interval.
And then on the closed interval, if it was like a parabola, I heard you say briefly, I just want to make sure I heard right. It can have two maxes or two mins.
Two locations of them? Yeah. So like,
okay.
It wouldn't have.
Like the y would be the same, but the x's would be different. Okay.
Yes. Yeah. So that's, yeah, and thank you for bringing that up too. Because sometimes that gets a little confusing when you're talking about the actual absolute extrema value. That is always going to refer to the y value, and the location is always going to refer to the x. So when we say we have an absolute max at like 8, that's talking about the y value of the point. So for this one, yeah, you do have a relative, absolute max, and the max value would be at 8, and it occurs twice. So at x equals 2, and then another one at x equals 10. And then the min, there's just the one value at 3, and that occurs at x equals 6. So there can be more than one location, but there's always going to just be the one actual max or the one actual min value. Okay. Okay, so the process for finding the two, they are pretty similar, at least in the beginning, but for the absolute, it kind of like it deviates a little bit, and there's like more stuff you have to do to tell if it's an absolute extrema or not. So how do you find an absolute extrema? If you're not looking at the graph, like I just gave you a function and said, find the absolute extrema from here to here, how do you do it?
Find the critical numbers and then evaluate at the critical numbers and the endpoints.
Nice. Okay, so let's let's go with f of x is equal to, let's do x squared minus 6x plus 9. Just kind of make it easy. Over the interval 0 to 4. Okay, so she was exactly right. So find your critical number, so that means you need the derivative. So what's the derivative of that function?
2x negative 6.
Yeah. And then if you set it equal to 0, x would equal 3. So right there, there's your critical number. And now you have to go, or now you have to test them to see which is going to yield the largest and the smallest values. So where do you plug them back in? Do you plug them back into the derivative or something else?
In the original function?
Yeah, back into the original function. Anytime you're looking for the y coordinates, you're always going to go back to the original function. If you plug it back into the derivative, especially if you plug those critical numbers back in, it's going to make your derivative either 0 or undefined, because that's what you just solved it for. So plug them back into the original function. So f of 0, f of 3, and f of 4. And then we'll see which one is the biggest and which one is the smallest. So f of 0 is going to equal
9.
9. F of 3.
0.
And f of 4. Say it again.
1?
Yeah.
I think. No.
Oh, yep. Good old arithmetic. That is where most calculus students make their mistakes, is just the arithmetic, just because it's so easy to do, and the professors too. All right, so the f of 0 is equal to 9. So again, the max value itself is 9. And the location would be the x part of the coordinate. And then your absolute min would be 0, and that's happening at x is equal to 3. So that process that we just went through, that's the same process for every single question you would ever have on, like, where's the absolute extrema, or find the absolute extrema, or whatever they're going to ask you about it. That's pretty much what you're going to do. Where it changes is the derivative part, because you might have to use a quotient rule or product rule or chain rule or something like that. Okay, so any questions on the absolute extrema? Okay.
Oh, I have one question.
Oh,
If the interval was an open interval and not a closed interval, would you still evaluate 0 and 4?
So if it was like that?
Yeah.
If it was this question, that would be a trick question, because there would be, you might not have an absolute max or an absolute min. So in this case, there would be an absolute min because it's occurring inside that interval, but there wouldn't be an absolute max.
Okay.
But I wouldn't do that. it would have to be something like this. Like I would just give you the function and the closed interval, and then there would have to be a max and there would have to be a min. So like on the quiz, when it said, find the absolute min, absolute max, and then if there wasn't one, put none. No one should have put none because there had to have been both of them. If it's continuous and it's closed, you are guaranteed to have an absolute max and an absolute min, unless it was that horizontal line case, which it was not. Okay. All right, now let's go ahead and talk about relative extrema. Okay, so run me through the process just kind of quickly on how you would find relative extrema.
You could either use the first derivative test or the second derivative test.
Okay.
And if you use the first derivative test, you would find the derivative of the function, find the critical numbers, set up the number line thing that you showed in the notes,
Okay.
and then test values on either sides of the critical numbers. And then once you do that, if it switches from negative to positive, then it's a minimum or relative minimum. And then if it switches from positive to negative, then it's a relative maximum.
Nice.
And I don't get how the second derivative test is used. Can you explain that?
Like how it's used or how it determines?
How it determines.
Okay. Yeah, the second derivative test, between the two, to me, the first derivative test is way more applicable, especially in this class. The second derivative test, like it's nice, but it has that little caveat that, well, if it actually makes the second derivative equal to 0, then the test fails, which a lot of times it does. So the usefulness for the second derivative test really isn't going to come into play so much, or you're not really going to use it as often until you get to like the tail end of calculus 2, and then some again in calculus 3. But to introduce it in calculus 1, just kind of get you used to it, so you go, oh yeah, that's what it was. Okay, whoops. Second derivative test. Okay, so the second derivative test said, all right, you plug in your critical number into the second derivative. And if it came out as 0, was that a max or was that the min? Or sorry, if it came out as positive, was that the max or the min?
That was the minimum.
That was the minimum. And then if it was less than 0 or negative, that was the max. So it is counterintuitive to kind of what you would think it would want to do. But this is why. Because if the second derivative is positive, what does that tell you about the function?
It's concave up.
Yeah.
So if you like imagine a parabola, there's actually a minimum there.
Yeah. So yeah, it's concave up. So your critical number, since it's going to be down there, that's why it's in this relationship. Where so if the if it's concave up, then you have to have a minimum. Okay, so does that answer your question as to how it works the way it does?
Yeah.
Okay.
Thank you.
So on the exam, I'm not going to tell you to use one test over the other. It's going to be up to you. So if you want to use the second derivative test, you're more than welcome to. To me, it's just easier if you use the first one, because you're having to find all this data anyway. So all that stuff is like right there for you to evaluate. So you might as well use what you have. But if you want to use the second derivative test, then totally go for it. Okay, so let me go back up to here where into that process. A lot of people, what they want to do is they want to just solve for the derivative equal to 0, and then they just sort of stop. Like I've just said, how many critical number or how many relative extrema are in this function? They just find the critical numbers and then they stop. And then they don't actually test them to see if it really does yield an extrema or not. It's like how many relative extrema does f have if f prime of x is equal to x squared times x minus 1 times x plus 2. So right here, you're given the derivative, you're not given the function. So you're already provided with the derivative. Now you just have to solve it. Solve it for 0. So your 3 different solutions would be what, and what.
Zero.
Yeah, 0.
1. -2.
Yeah. And so they'd stop there and they go, okay, so there's 3 relative extrema. But they don't know that for certain because they haven't run through either of the tests to see if it actually is or if it does yield a relative extrema or not. So you got to test them. So you got to go through that test. Let's just use the first derivative test. Okay, so give me some test numbers. Like anything that's smaller than negative.
-3.
-3. Okay, something between -2 and 0.
-1.
Between 0 and 1.
0.5.
And bigger than 1.
2.
2. Okay, and now these test numbers, these green numbers, where are you going to put them? Like, where do you test them?
In the first derivative?
In the first derivative. All right, so if you plugged in the -3 into all these x's right here, how does it come out? Does it come out as a positive or as a negative?
I got a positive.
Okay. And for the -1?
Negative.
The 0.5, or you could also use 1/2.
Negative.
Okay. And for the 2?
Positive.
Positive. All right. So the extrema, the relative extrema happen when there's a sign change and there was no sign change at the 0. So your relative extrema only occurred at the -2 because it changed from positive to negative, and then again at the 1 because it changed from negative to positive. So your answer would be there are 2. So just make sure that you're testing them to see that they actually do yield an extrema or not. Because most of the time they will, but every once in a while there's one that doesn't. And the same would go for inflection points. I said how many inflection points, you're pretty much doing the same thing just with the second derivative, but you still got to test them. Like, don't just solve it for 0 and stop. You got to test them first. All right, let's try one of these. Or actually a couple of these. So sketch the curve based on just criteria that you have. Okay, so first criteria is f is continuous. We'll say that the first derivative is negative. For x is less than 2. The first derivative is positive. For x is greater than 2. The second derivative is negative. For x is less than 2, and it's negative. For x is greater than 2. Oops. And then f prime of 2. So if you plug 2 into the derivative, it does not exist. So you can sketch any curve that you want as long as it matches up to these criteria. Okay, so let's kind of just break down what each of these criteria mean, and then we'll try to put it all together into a graph. All right, so the first one was that f is continuous. So what does that tell you about your graph or your sketch?
There's no asymptotes.
There's no asymptotes, or what else? So no vertical asymptotes. What else can't be in there?
No sharp points.
That would be if it said f is not differentiable. Or sorry, yeah, f is differentiable, but since it's continuous, it could have a sharp point in there. It just can't have a vertical asymptote.
Like holes.
Yeah, no holes.
Jumps, skips,
Yeah.
horizontal asymptote.
It could still have a horizontal.
Oh, yeah. Thank you.
Yeah, so nothing that like breaks your graph apart into two pieces. Okay, so it's going to be when we draw this, just one fluid continuous curve. All right, what about when it says the derivative is negative when x is less than 2? What does that tell you about the function?
It's decreasing.
F is decreasing. Okay, and then if the derivative is positive for x is greater than 2, what does that tell you about the function?
It's increasing.
Increasing. All right. What about if the second derivative is negative?
Concave down.
Concave down. And then it's still concave down at x after x equals 2. Okay, and then the last one, the derivative at 2 is undefined. It does not exist. So what does that tell you about your function? Like what might be happening there?
An extra relative extrema.
Say it again.
I'm deducing that the tangent line is 0 at that point, so it's a relative extrema.
Okay.
And I'd probably say it's a max because f prime is concave, f double of the second derivative is concave down.
Okay. Well, but you don't know the sign of the second derivative at 2. You know what's
Yeah.
happening around it, but you don't know the sign at 2 itself.
Yeah.
But there's something else that we could use to tell us like what type of extrema it is.
Maybe the first derivative transition.
Mhm. Yeah, because as you move from left to right, like the function is decreasing and then it's increasing. So it's switching from going down to going up. So that has to mean it's a what?
A min.
A min. Okay. Now, when we draw it, around that relative min, is it going to be doing something like this, like a parabola?
Oh,
It'd probably be sharp.
Yeah, it has to be sharp. And how do we know that?
Because the value of the first derivative doesn't exist. So,
yeah. Mm-hmm. Exactly.
So the limit is agreeing, approaching from either side.
Yeah. Mm-hmm. Yeah. Because it's continuous and the derivative doesn't exist, it's got to be some sort of a sharp point. And it's occurring at x equals 2. All right, so when we start to draw, we know that f is decreasing, so it's going to go down. So when you say that the function is decreasing, it can decrease in one of two ways. It can either go like that, or it can go like this. So out of the two, which one do we have?
the first one?
It's the first one. How do we know it's the first one?
because we also know that it's concave down.
Yeah. So that's where the concavity is going to come into play with these when you're sketching your curves, because it'll tell you like how, how it's curving around. So we know it has to be concave down. So it has to be this one. So it's decreasing until it gets to x equals 2. And then when it gets to x equals 2, it switches and then it increases. And we know it has to be that sharp point. And the graph, like it could be shifted up or it could be shifted down. That part doesn't matter because you don't have that much information about it. And it's just a sketch. So it's decreasing. Oops, I guess we could put it in the 2. Decreases to 2, and then it increases. It's concave down on either side, and the derivative does not exist at the 2. Right. Nicely done. Okay, any questions on that?
No.
In the text, on these questions, it would say like for the answers, like the vertical translation is really like loose. You can kind of draw it as tall, or small. Yeah, would that be true for questions we'd experience in this course moving forward?
Yes, if I understand what you're asking. Yeah, it's not really like it would come into play if you had other, like if you knew other function values. Like if I told you that like f of 2 is equal to 0, then now you know it has to be an intercept. But yeah, the like how tall, how skinny, that type of stuff's not really going to matter so much with this stuff, because I mean it's really just a sketch. We're not trying to be too precise with it, and we can't because you don't have that much info to go off. So all you can do is figure out like how things curving around, and that's about it. And where extrema happens, if there's asymptotes and whatnot.
Okay, thank you.
All right, so this one, it's going to be the same criteria in part A. So all this stuff is going to be the same again, but I'm going to add in a couple of different things. We're going to say the limit as x approaches negative infinity of your function, that's going to equal 5. And then the limit as x approaches positive infinity of the function, that's also going to equal 5. So how is that going to alter the graph that we just did?
So it has a vertical asymptote?
Which kind?
Vertical asymptote as 5?
I like the asymptote part, but it's not vertical.
Horizontal, sorry.
Horizontal, yeah. So you can do basically the same type of curve. Just kind of flatten it out as it goes off to the left and it goes off to the right, and have it approach that y equals 5. Nice job. So if it tells you something like this, where it throws in a limit as x approaches negative infinity or positive infinity, that means now you have some sort of a horizontal asymptote happen. Okay. Any questions on that one? Okay. All right, let's talk about some of these limits. Okay, so let's go the limit as x goes to infinity. I don't know, 7x squared plus 2 all over 8x squared minus 9. All right, so these types of functions, as long as the degrees are equal, then it's just the ratio of the leading coefficients. So in this case, it would just be 7 over 8. Would it still be 7 over 8 if you approached negative infinity instead of positive? Or would it change to now negative 7 over 8?
It would stay the same.
It would stay the same. So typically it doesn't necessarily matter which one you approach, you're still going to get the same result. But typically, so if you had like this one, uh, 3x plus 2 over the square root of x squared plus 5 as x goes off to infinity. You can still use that degree trick. You just have to look at what's inside the square root first and square root it. So you're just paying attention to the highest power that's inside of there. So you can ignore the 5. So just drop it out. And just do the square root of x squared, which will just give you x. So the degrees match up again. They're both 1. So it would be the ratio of the leading coefficients. So 3 over 1 or just 3. And then we have everybody's favorite, where x goes off to negative infinity. And this is where you do have to be a little careful, because you are still going to do that same trick like we just did. You know, square root the x squared to give you x. But this one is going to be negative 3. So why is this one negative instead of positive?
Because you're multiplying 3 by a negative number and you're squaring a negative number and getting a positive on the bottom.
Nice. So this one, yes, exactly right. You do have to pay attention to what x is doing. So x is approaching negative infinity. So those are all those negative numbers. So on the top, she's right. A positive times a negative is a negative. And in the denominator, you're squaring it, which is always a positive. And then you square root it, which is always a positive. So negative over a positive gives you a negative. And then don't just think because, oh, it's going off to negative infinity, that's why it's a negative, or that it will always give you a negative. because if it was that on top, now it's going to flip it back to positive 3. Because now you have a negative times a negative, which is giving you a positive. The denominator is still positive, so now it's flipped back to a positive 3. All right, let me do one more of these. About the limit as x goes to negative infinity of 3 e to the x. What do you think that's going to do?
Is it 0?
It's going to go off to 0.
And that's because you plug in the negative infinity to e to the x. It flips it into a fraction.
Yeah.
Which is, it's 3 over infinity, which is basically 0.
Yeah. Yeah, 3 over infinity or 3 over a really, really big number is going to pull that fraction down, 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 and closer and closer and closer to 0. All right, nice job.
What do you, I have a question. What do you want us to do on the evaluate the limit ones where the, where you might have like x cubed over x squared and you have an oblique asymptote? Will you ask that in that type of question?
Like where you have to evaluate it, or are you asking if you have to find the oblique asymptote?
No, you have to evaluate it. So if I had like, if you take the b and made it 7x cubed minus 2 over 8x squared minus 9, that would be.
So like that.
I'm sorry, it's really small on my screen. Oh, I think so. Yeah. Yeah.
7x to the third plus 2 over 8x squared minus 9. That would just be infinity. Because now the numerator has a bigger degree. So now it's like the numerator is the boss and it's telling everybody else what to do. So it's going to go off to infinity. There is an oblique asymptote there, but like it's not asking you to find where it is. It just wants to know if it's going off to infinity or what it's doing. And then if it was going off to negative infinity, the numerator has the bigger degree, but where is it going to go? Is it still infinity, or is it now going to be negative infinity?
Well, the negative infinity, because it's cubed.
Yeah.
Thanks.
Sure. And just as a side note too, if this question popped into anybody's head, she was talking about an oblique asymptote. I'm not going to ask you to find out where something has an oblique asymptote. You can find it if you want to, but it's not going to be something I'm looking for on the exam. Okay, let's see, any other questions on the limits?
No.
Okay. Okay, let's take this graph and we're going to have it represent the derivative. And it's bouncing on the origin. It reaches its relative max, or reaches the top of that curve, -4,6. And then it has another x-intercept at, we'll just make it symmetric, -8. So this is the graph of the derivative. And the question is going to be, where does f have a part A, relative min? And there will always be two answers I see for this question, and only one of them is right.
-8.
-8. What do you think the second answer I see is usually?
0.
Yeah, right at 0. Because they're going, oh, it's a relative min right here. It's like, well, yeah, but that's where f prime has a relative min, not f. So it's not asking you to analyze this graph right here as you see it. It's asking you to analyze a graph that you cannot see using this. Okay, so what would be your justification? Like, why is it at -8?
The derivative is negative as it's approaching -8, so the function is decreasing, and the derivative is positive beyond -8, so the function is increasing.
Nice. Okay, so it's switching from negative to positive, or you could say, actually, yeah, you could just say it just like that. Okay, so using the graph of the derivative, where does the function, or f, have a relative max?
Doesn't have one?
Doesn't have one. Because it does not switch from positive to negative. Okay, so next type of question would be like, where is f increasing?
From -8 to -4, and then from 0 to infinity.
So -8 to -4, and then from 0 to infinity?
Yeah.
That's close. So how come you left out the section from -4 to 0? Because it went down?
Yeah, because it goes down.
Okay, so that's where the derivative goes down. That's not necessarily the function though. So if I would have said, where is f prime increasing, that would have been almost right. But I want to know where f is increasing. So again, you can't look at where this graph is going up. because that's not the function.
Can you think of it like the slope of the tangent line of the original function for that period of time where x is between -4 and 0 is actually flattening out for a little while?
For the
Like
original function?
Yeah, from the original function, if you visualize the original function and you were mentally drawing all the tangent lines on the original function, there'd be from -4 to 0. The tangent lines for that period of time were getting flatter and flatter, or going down, I should say.
It's, yeah, they kind of, because they're still positive.
Yeah, they're still positive. They're just getting closer to
Yeah,
horizontal.
just sort of, it kind of like starts to tilt and then kind of back down and then tilts.
Yes, exactly. Yes.
Yeah. You can think of it like that. But for these questions too, you do have to go back to your definitions, and how you tell like where a function is increasing. Because if I give you a function, most people can run through, get the derivative, find the critical numbers, and then they start testing where things are positive or negative. So if the function is increasing, what does that tell you about the derivative? If the function is increasing, what do you know about the derivative itself?
It's positive.
It's positive. So when you translate to the graph of the derivative, if I say the derivative is positive, where are you looking?
From -8 to infinity?
Yeah, because that is where it's above the x-axis. So yeah, -8 to infinity. It does hit the 0 here, but it doesn't go below. It doesn't go negative. It just hits it and goes right back up. So there was no direction change. So using this graph, now if it said, okay, well, where is the function decreasing?
From negative,
that's telling you to look for where the derivative is negative, or where it's below your x-axis. So somebody was trying to say where that was.
-8. I mean, from negative infinity to -8.
Nice. Okay, so any questions on that increasing, decreasing part?
How come it doesn't matter if it's negative relative to the y-axis, but to the x-axis? Because that kind of trips me up.
Say that again. How come this doesn't matter for what?
So f prime is positive above the x-axis. How come it doesn't matter if it's negative to the y-axis? Does that make sense?
It's negative. So like how come it doesn't matter like if it's just on the negative x's?
Yeah.
Because when you're talking about the function itself, does that refer to the x values or the y values?
The y values.
Just the y values.
Okay.
So the x's are like what you're plugging into it, but if it says, hey, what are the function values or what are the derivative values, that's always talking about the y's.
Oh, that makes sense.
Because you had to plug an x in there to tell like what it was.
Mm-hmm.
Okay, any other questions on the increasing, decreasing?
Are you ever gonna, is it possible you might ask us to actually generate the derivative graph, or is it primarily gonna be interpret the first derivative graph?
I could ask you to generate the original function.
Would it be an estimate of the original function, or do you feel like from this amount of information we'd be able to actually generate the original function?
You can't generate the exact original function. You don't have enough information.
Okay. But you might ask us to generate an approximation of it.
Yeah, that's why it's always called a sketch.
Okay.
Because you don't have enough info to get the actual function.
Yeah.
So, I mean, if you want me to, I could give you enough info where you have to give the exact function. But you probably don't want me to.
No.
Yeah. All right. Okay. So so based off of this derivative graph, where is f concave up?
From negative infinity to -4, and then from 0 to positive infinity.
To -4. And then what was the second part you said?
From 0 to infinity.
Nice. And then what would be your justification?
Since f is increasing, first derivative is increasing.
Nice. Oh, forgot the justification for the increase and decrease. Okay, and then the flip side of that, where is the function, not the derivative, where is the function concave down?
From -4 to 0.
Yeah. Since
First derivative is decreasing.
Nice job. All right, any questions on the concavity part? Okay. All right. What things do you want to go over, or what are your questions? As I said, I would do stuff for about the first hour, and then the rest of it would be up to you guys.
Are you going to ask us to sketch graphs of like trig functions, exponentials, and other complex ones like arctangent?
Probably not an inverse trig function, but I could give you like a regular trig function, like a sine or a cosine, polynomials, some rational functions. Actually, let me ask you this. Are you talking about like if you have the function itself, or are you just going off of the graph?
I guess both now, but mostly going off just the function, not the graph, function. And you have to sketch everything out and find the data.
Oh, okay. yeah, if I give you the function, polynomials are definitely fair game. Some rational functions, like if there's like one vertical asymptote in there, or maybe two. Not an inverse trig function. Exponentials, like the base ones, not anything too crazy. Like I'm not going to have you sketch something like, oh, I don't know, e to the x times sine of x or something like that, or e to the x to the sine of x. Nothing not that complicated. But a basic exponential like e to the x or 2 to the x, that's totally fine. Ln of x or ln of x minus 1, that would be okay as well. Some people on the last quiz, I can't talk about that yet. It's not new. So yeah, I'm not going to ask you to graph anything too far out there.
Okay.
And the same for like if you were given a graph. Let's say that was your function, and it said graph the or sketch a possible derivative. What would you end up drawing?
I have no clue. I need to study these.
Okay. There are a few ways to do it. One of them, to me, which I like the best, is to sort of cheat at it. So like this function right here, it's definitely a polynomial. And what would be the degree?
Probably the third.
Yeah, it's an x to the third. If it's n shaped, that's going to be some sort of an x to the third. There's going to be other terms in there too, but we don't care about those. Because they don't tell you how to draw the derivative. It's the first term of the polynomial. So if it's an x to the third, what would be your derivative?
3x to the second power.
Yeah, 3x squared. So you know that your derivative is going to be some sort of quadratic. Well, what's the graph of every quadratic?
A linear function.
A what?
A linear function.
The derivative of a quadratic is, but what's the graph of every quadratic?
Oh, it's just a parabola.
It's just a parabola. So you know you're going to have a parabola on here somewhere, and you can't get too specific about it, but you can get really specific about the intercept, where the derivative is going to hit the x-axis, because that occurs anywhere you have a relative max or relative min, because that's where the derivative is equal to 0. So for me, when I draw them, I look for any relative extremo, and I just drop them down or pull them up to the x-axis. And now I've got my derivative intercepts. And so now I can draw my parabola right where it needs to go. And again, I'm not going to judge you on like how far down, how skinny this thing is. As long as it's the right shape and you have the right intercepts, that's totally enough.
Okay. Someone from the chat asked you to solve a problem from section 4.7, the optimization one.
Oh, thank you. Okay, that was from where?
They just said an optimization problem, 4.7.
An optimization problem?
Yeah.
Hang on a second, let me grab the book. So I can make sure I do one that actually works. So trying to make one up off the top of my head and giving an impossible problem. Oh, all right. Okay, so this is from page 262. Let's do number 13. It's like most of these optimization problems are really similar to each other because you kind of have to go through the same process. It's just the setup for them could be different because they're just different scenarios with different equations. But once you get it set up, then everything is kind of similar from there. So this is find the point on the graph of the function that is closest to the given point. So our function is x squared and the point is 2 1/2. So just to visualize, here's your curve. We'll say 2 1/2 is over there. And it's asking, okay, well, if you took a point that's on this curve, which one is going to be closest to that point of 2 1/2? All right, so for these optimization problems, the thing that we went through in the notes was finding your two separate equations, your primary and your secondary. If you have another technique that you've learned from somewhere else, you can totally use it. You don't have to use this primary or secondary stuff. That's up to you. All right, so let's figure out what the primary is. So when they say closest to something, like what would be a good type of equation that would go with that?
The distance formula?
The distance formula. Good old distance formula. And what is the distance formula?
Square root of x2 minus x1, and that's squared, plus y2 minus y1, that's squared.
Yeah. Okay. And what about a secondary?
The provided function
Mm-hmm.
kind of acts as like a restriction.
Yeah. Yeah. So your secondary, if they've given you some sort of a function, that's probably going to be your secondary. So we'll also make it y equals x squared. All right, so let's take our primary and start plugging in everything we have. So when you start plugging stuff into the into the distance formula, you got to plug in your 2 points. So we're going to take the one that they gave us, the 2 and the 1/2, and then we're also going to take the point that's on the curve, the xy. So we'll make the x the x2 and the 2 the x1. And then the same thing for the y's. And we're going to need to take the derivative of this stuff, but we don't want to do that until all of the variables are the same. And that's why you need your secondary, so that you can get everything in terms of either X or get everything in terms of Y. So since you already know that Y equals something, let's just go ahead and use it. So we'll plug the X squared into this Y. And now you've got everything in terms of an X. Okay, and since we have two annoying quantities like this, let's just go ahead and FOIL them out. So that'd be X squared minus 4X plus 4 plus X to the fourth minus X squared plus a fourth. And then you can combine your like terms. So we'll move the X to the fourth to the front. The X squareds, excuse me, they cancel out. So X to the fourth minus 4X. And then we have 4 plus a fourth. So 17 over 4. Excuse me. So once you get your primary equation down to just one variable, what are you going to do with it?
Take the derivative.
Mm-hmm. Take the derivative and then set it equal to 0. Well, with things like this, like when you have the square root and everything's inside of the root, if you're trying to maximize or minimize the radical, you can get away with just maximizing or minimizing the stuff that's inside the radical. So we're just going to take the X to the fourth minus 4X plus 17 over 4, and we're going to maximize or minimize this thing. So you can ignore the radical. If you had stuff outside of the square root, you cannot do that. But since it's totally inside the square root, you can get away with it. So what would be your derivative of this?
Four X to the third minus 4.
Yeah. And set that equal to 0 and solve for X. So X to the third has to equal 1, which means that X is going to equal 1. So you're almost there. So find the point that's closest to it. So you have your X. What's the other thing that you need? If they're asking for a point, what else do you need? Because right now you only have half of your answer.
The Y value?
Yeah, you need the Y value. So what are you going to use to give it to you?
The secondary equation?
Yeah, the secondary. Either the Y equals X squared or the F of X equals X squared. Either one, so that comes out as 1. So the point that is on this curve that is closest to 1/2 is the point 1, 1. So all of those problems that are in that section, they're basically just kind of like this. You have a primary, you have a secondary, you get your primary all down to one variable if possible. Take its derivative, set it to 0, get your critical numbers, and then find out which one gives you the max or the min. And just to put your minds at ease, you're not going to have like 8 questions on this one section. Like you'll have 1, maybe 2. So don't spend the bulk of your time trying to study 4.7 because there's 6 other sections that are in there that you also need to pay attention to. So this is only part of the exam, it's not the entire thing. All right, what else would you like to go over? And what other questions do you have?
I know you said you're not going to require us to know the exact oblique asymptote. When I started doing the even problems on 4.6, it came up. And I found that in order to draw it correctly, I had to do the long division and figure out the oblique asymptote. I guess I'm trying to figure out if that's
what
something.
Some people do with those.
Yeah.
So say like there is an oblique asymptote like this.
Yeah.
And the curve is supposed to look like that.
Right.
What people do, and I'll accept it, is they just go like this. Because that's still concave down, that's concave up. It's matching the increasing to decreasing, decreasing to increasing. The only thing that's missing is the oblique asymptote.
I see.
So it's like, don't stress too much on getting the oblique and trying to be so exact in your graph. Because again, it's just a sketch. I was like, it's hard, especially if you're so used to being very precise in your curves and you want to be, but it's like just sketch it as best you can. So if you want to throw in the oblique, you can totally do it. It's not going to count against you. You just don't have to. If I had like another week of class, I would probably go through it and then expect you to find it, but there's just not enough time.
Do you have any fun like pop theorem questions on hand that we can maybe go over together?
Pop theorem type questions?
Yeah. Like true, false, or does this represent this kind of questions?
Let's see. Oh. Just really quick. How do you find the relative extrema of velocity.
Find the critical numbers on acceleration.
Yep. Because anytime you want the relative extrema of anything, you find its derivative, set it equal to 0, and get the critical numbers. So in this case, because it was specific to what it was, she is exactly right. Set acceleration equal to 0. Get critical numbers. And then I would use the first derivative test. But if it's anytime, find the relative extrema of this, then you need to take its derivative, set it equal to 0, get the critical numbers, and then use that first derivative test. It doesn't matter what it is. It could be, what's the relative extrema of the fourth derivative? Then you set the fifth derivative equal to 0, get it, those critical numbers, use the first derivative test. All right, does Rolle's theorem apply to f of x is equal to 1 over x minus 1 on the interval two to three?
No.
That is correct. Why not?
Because it has a vertical asymptote.
It does, but that's not why it doesn't apply.
The n values aren't the same.
The n values are the same because you're right that there is a vertical asymptote, but it doesn't occur in the interval. So it is continuous from 2 to 3. It is differentiable from 2 to 3, but f of 2 does not equal f of 3. Okay, how about does the mean value theorem apply to f of x is equal to tangent of x on the interval from 0 to pi?
Yes,
Okay, how come?
it's continuous and differentiable.
Okay, does tangent have a vertical asymptote?
Oh, I'm sorry. Yes, at pi over 2.
So does that change your answer?
Yeah. Oh, yeah. Doesn't. I thought you said something other than tangent.
Oh, okay. Did you think I said cotangent?
Cosine. Yeah. I thought you said. Yeah, I thought you said something else. Yeah.
Oh, okay. Yeah, if it has a vertical asymptote in the interval, then you cannot apply the mean value theorem or Rolle's theorem. What is the difference between the two theorems criteria? Because they're similar, but not exact. Like they have different conclusions, but they start out somewhat similar. So what's that, like when they start out, like the criteria that you have to run through to check to see if they apply, how are they different?
With Rolle's theorem, with having the endpoints be equal at some point, at some C, the tangent line is 0.
Yeah. So that's where the criteria varies. That Rolle's theorem has that extra little caveat that the endpoint values have to be the same. But both of them, you have to check to see, okay, is the function continuous and is the function also differentiable? But for the mean value theorem, that's all you have to do. And then you can actually use the theorem. Rolle's theorem, you have to make sure that the endpoints are equal, and then you can use the theorem. Let's see. If the first derivative is increasing on a to b, then the second derivative is positive, and f is concave down on a to b. Would that statement be true or false?
It would be false.
Okay. So what makes it false?
Because it states that the second derivative is positive, which is concave up. And then you say the graph is concave down on a to b, and those contradict each other.
Nice. Yeah, so to make it true, it either have to be second derivative is positive and concave up, or second derivative is negative and concave down. Okay, let's try this one. If f is differentiable on 0 to 5, then f is differentiable on the closed interval from 1 to 4. Would that be true or false?
I would say true.
That would be true. Yeah, because as long as this closed interval fits inside of the open one, then it's going to be true. Trying to think of like other little pop theorem type questions. It's like, I think that's about all I can ask since this week's quiz hasn't closed yet. So I can't give any of those questions out.
I was going to ask a question on that. Remember we did the derivative graph from -8 to 0 and then on to infinity.
Yes.
While we were sitting here, I just attempted to sketch the original function. Can I email that to you and see if I had it right? Because I think if you ask me to convert from the first derivative to the original function, it's going to take me a really long time and slow me down on the exam.
If I have you go backwards?
Yeah, I'm having trouble going backwards from the first derivative to the original function.
That way is usually a little bit trickier, but you can still kind of cheat at it. What is that? Was the max at -4?
Yeah, -4 on the x-axis and 6 on the y-axis.
Oh, okay. And the intercept was at -8?
Yeah, -8 and 0.
0. So the derivative in this case, that would be like an x to the third, because it's in shape, so it's a polynomial of degree 3. So that means f would have to be what degree? Fourth degree. Because polynomials are kind of nice. Their derivatives are always 1 degree less. So if the derivative is a 3rd degree, then their original had to be a 4th degree.
Mm-hmm.
And 4th degree polynomials typically look like what letter of the alphabet? 3rd degrees look like N's. 4th degrees, they also look like a letter. Anybody know?
W?
A W. Typically, not all the time, but most of the time they do. And if it was negative, it would flip upside down, and now you've got an M. So with this one, since the derivative is switching, excuse me, from negative to positive, that's where you've got a min. So your derivative graph, or sorry, your original function is going to have a min somewhere. I don't know, we can just put it down here. I guess you could shift it up or down, depending. So that would be this one. And then you could try to like find the other two extrema, like the max and the other min, but it doesn't do anything else. Like there's no other sign change. So we just have this one min. So what that does to your polynomial is instead of looking like a W, it's kind of like this section gets merged together. And it's going to do something like that. And so where that slide right here is occurring, that's where this critical number here is going to happen. So that's why there's no sign change there, is because you had some sort of a slide in your original function.
Mm-hmm.
So I would sketch it doing something like that.
Okay, and on the point where you, oh, I see. So you took the intercept on the negative side at -8 and moved your point down.
I did.
Okay, help me out
I mean,
there.
you could shift this whole thing up too if you wanted to, but the minimum has to occur at the x equals -8, and the slide would have to occur at x equals 0.
Okay, that's where I messed up because I shifted negative. I drew exactly what you said, that kind of wonky W. But I drew it above the x-axis, not deducing that a 0, 0 was a value of the original function.
Okay, I mean, you could do that too. You just don't. It would be hard. It would be really difficult to find the exact function because the only y value you have, I guess you have like, it's like you'd in order to find the exact function, you'd have to know the exact derivative and a point of the actual function, which you don't have.
Oh, okay. So is my wonky W above the x-axis still okay then? Like
So
the
like
fact that, yeah, go ahead and draw it. Imagine your green one, but shifted above the x-axis.
like all of it above there. Oops.
Yeah, all of it.
So it could go like that.
Yeah. That's what I did. Something like that. Would that be valid?
Sure.
Okay, good. Okay.
Because it's still matching up to what it's doing. It's decreasing until you get to -8, and then it switched to increasing, and then it increased the entire way from there on out. So yeah, that would be totally fine.
Okay. Thank you. Thank you.
All right. Well, I think that's all the time I've got. So if you have any other questions, just please email them to me and I'll be able to get back to you with an answer. If you haven't done it yet, I would encourage you to take the quiz, this last quiz, so you're not trying to do everything all at once. And it'll help you to study too. Kind of, if you see a question on the quiz and go, oh, I should study that. It's nice to know that on a day or two ahead of time before you take the actual exam. All right. Well, thank you for coming. It's nice to be able to talk to people and to see some of your faces.
Thank you so much.
You're welcome.
Thank you. Have a great
Thank
day.
you. Bye.
You're welcome. We'll see you later. Good luck on the exam.
Thank you.
Thanks.
Bye.